let's talk about FSM, or finite state machine, right? So this is a brand new topic, and this is also an important topic. We're going to be looking at FSM a lot, right, later on. And later on, when you guys design a complex digital system, you always need to design something called a controller. The controller is basically FSM. So what exactly is finite state machine? It's basically the abstraction for sequential logic. Now, we have been talking about abstraction a lot, right? So it's basically the abstract model of sequential logic. So if you think about sequential logic, now we have, right? So we usually have these stateful elements, right? The flip-flops, right? And then we have some additional logic that computes the next value of the flip-flop, right? So that's basically what this diagram is saying. Okay, we have this feedback, right? So for sequential logic, we always have the feedback, right? And then we have this state which capture the current or paths, right, of the circuit. And we need some additional logic, right? We need some additional gates, right, to update these flip-flops. Okay, so this is basically an FSM, right? Like I said, this is a model, and this is an abstraction of a sequential circuit. And it's very useful for us to reason about the sequential circuit. So we have something called state, right? This is something that we already familiar with. And we have something called next state. Okay, so this is not something that we introduced in the past, right, in before. So this is something that we need to understand very clearly from in this lecture. So we have something called next state and current state. I'm gonna make it a lot more concrete. Okay, and we have this conditional logic, right, that update the state, right, and also determines output, right. We always want to output something, right. So this is basically the signal to the outside world. And we will see actually there are two flavors of FSM. So in one flavor, the output depends on just the current state. In another flavor, so the first flavor is called Moore machine. Okay, the second one is called Mealy, right? Named after two American scientists, right? Edward Moore and George Mealy. Okay, they are actually the pioneers, right, on this this topic, FSM. Here's a question. Almost asking, is state just a buffer or implement logic on the next state output by the green box? Good question, right? So first, this is, we are talking about the abstract notion here, right? State basically, if you look at this, right, embodies the condition of the system, right? It basically literally capture the state of the system, right? And then if you talk about how we actually implement the state, right? So last time, right, so we talked about flip-flops, right? Flip-flop is one of the physical implementation of this state. Right? We can actually, right, store values, right? We can save value and hold values using flip-flops. Right? Of course, you also talk about latch, but going forward, like I mentioned, we'll most likely just focus on flip-flops. Okay, the reasons will be very clear later on. Okay. Oh, and also one more thing I should have mentioned. Let me go back here. Okay, so one more thing. Here it is. So in many cases, right, so when I draw a circuit like this, or in the homework and exam, we assume that there's a clock. Okay, you assume the clock signal is connected, right? So it's not like the flip-flop is not driven by clock, right? That's usually the assumption. And that's how we can have the time, right? The notion of time. That's how we can advance the state. All right. Okay, so I think this is pretty abstract right now, right? Let's try to make it a little bit more concrete. Okay. But the key terms are here, right? Current state, next state, outputs, inputs. All right, so we'll talk about what exactly is current state and next state. Right? First, it's called FSM, right? Since we are building digital system, everything is finite. Right? Hopefully this is not a surprise, right? So we basically have finite number of inputs, finite number of outputs, right? Finite number of states. And also we have finite number of state transitions. We actually need to move between states. And this can be usually captured by something called a state diagram. So some of you might have taken some additional CS classes, right? So there you might have also noticed, right? Seen this notion of FSM, a finite machine or automata. Okay, this is the very similar. Okay, so what is sequential logic, right? Again, we have flip-flops and right, summation logic. So what about the DFF? DQ, right? DFF. This is very much sequential, right? This is a very basic sequential element. If you look at DFF and if you look at this diagram, so can you guys tell me first, how many states are we capturing with a single DFF? How many states can be captured? So how many states do we need to model a DFF? Let me rephrase. Okay, so we basically want to build a, we'll do that in the next lecture. I'll ask you guys to build a FSM state diagram for the DFF. It's a DFF, right, of FF flip-flop. So we talk about FSM is the abstract model of sequential logic, right? So then I'm asking you guys, how many states do we have? 2, right? 0, 1. We have this bistable, right? So same 0, 1. Okay, good. So and then let's try to map this template, right? This is a template. Let's try to map this abstract template to this DFF. So what do you think is the current state? What do you think is the next state? Which one is the current state, D or Q? Which one captures the current state? Very good. Q. Q is the current state, right? This one, this is current. Indeed, right? So this is what Q means, right? Q basically is the thing that this D flip-flop is holding, right? It's current. Make sense? The current state. What is the next state? Which one represents the next state? It should be obvious. D is the next, right? Again, makes sense, right? So after the clock edge, right, the state is going to advance to what D is, right? Q will be assigned with D. All right, so this is basically how we can map, right, this template to DFF. Hopefully now it's more clear, right, to you guys, right? What is current? What is next? Right, current state, next state. Okay. Of course, there's no more conventional logic, right, for DFF. There's just a single state element. Okay, so this is another form, another abstract form, but this is slightly more concrete, right? So now we are replacing the state, right? This state box with a set of flip-flops, right? That's how we implement things. Okay. Again, see here. So this is the D side, right? The input side of the flip-flops, and this is the Q side, output side, right? Next state, right, is connecting to the really D, right? Represent next state, and Q represent current state. And we have this feedback, right? So going into some conventional logic, which computes output. All right, so this is a general form. We can actually divide this, right? There are 2 different ways to implement. There are actually 2 popular ways. Let me put it this way. Okay, so to implement FSM, right? One's called a Moore machine. It's named after Edward Moore. So with a Moore machine, okay, it's actually about this a different machine, and the other one's a Mealy machine. So really the difference is how we compute outputs. It's really how we compute outputs. So for FSM, we actually need to update 2 things. One is the next state, right? So this conventional logic is computing, right? It's computing next state over here, right? For next state, we always need the current state, right? We need the current state over here, right? And we need the inputs, right, to compute next state. But for output, okay, so difference between Moore and Mealy. So I'm going to talk about Mealy for output. So with Moore, see here. So the output only depends on the current state, right? If you look at the arrows here, right? These are inputs, right? The inputs only influence the next state for Moore machine. It does not influence the outputs. The outputs strictly depend on the current state. That's the definition of a Moore machine. Right? Is it clear? Okay. It's really about output. So if this is not clear enough, right? So let's see the Mealy machine. So as you guys see the contrast, right? The distinction. For a Mealy machine, again, this is important, right? It's named after George Mealy. So again, next state, right? So no difference. Next state depends on both inputs and current state. But let's read the output. Okay, look at the output here. Output, of course, depends on the current state, right? And also depends on the input, right? So that's a Mealy machine. Okay, any questions? Right, so for Mealy, basically, if you look at output size, we usually connect to both input and current states. All right. So they're actually, and so these are the, this is the one way to look at this, right? So the more like the more hardware-centric way, okay, to look at this Mealy machine, the Moore machine, right? So we basically decompose here. We decompose the computer logic into two parts, right? So later on, when you guys write FSM, that's going to happen in lab 3. You will need to design an always block, right? One always block for next state logic, and another always block for output logic. Okay, both are conditional. So Lawrence asking, can you have an infer latch if you use registers and not wire? Laura, can you elaborate? What do you mean by if I use registers? So first, one thing that's important is register in this class always means flip-flop. Okay, so we do not distinguish DFF, FF, flip-flop, and register. They're the same thing. But in Verilog, we have something called REG, right? Reg. So that reg can turn into register, wire, or latch. Okay, make sure that you guys are not confused about this. Okay. So Laura, that side, can you elaborate? Can you clarify? What do you mean by if you use?
Yeah, I guess I was just going back to the example where you talked about like an inferred latch. I noticed how it just used like the equals sign and not like the arrow. So I was wondering if you replaced like out equals D and out you replaced it with like out arrow D, would that still be an inferred latch?
You're talking about the Verilog or Verilog code?
Yeah.
Right. So again, you're talking about combinational logic versus infer latch.
Yes.
This is not related to the FSM, right? First of all.
No.
Is it related to FSM? Is it related to this diagram?
No.
Okay.
Sorry.
Okay. So yeah, no, that's fine. So I'm just trying to understand the context. So again, in Verilog, right? So you want to infer flip-flop, right? Just use the you need to use clock catch, right? In the sensitivity list, right? If you want to specify conditional logic, right? You don't want to use clock, but you want to make sure that right under all conditions, the output is assigned, right?
Okay.
Otherwise, you have latch, right? But going forward, when you guys design your system, your actual circuit, right? You're going to design FSM, you're going to design microprocessors. So we are not going to be dealing with latches. So that's why I mentioned infer latch, right? So when you guys see the warning infer latch, that's bad news. Okay, get rid of that. Get rid of that warning. Okay. All right. So coming back to FSM, right? So we talk about this sort of hardware-centric view. Right? We look at flip-flops. Right? We look at the conditional logic, right? How they are connected. So let's also look at a different view. Okay, we can also represent this FSM using so-called state diagram. Something like this. Okay, so this is a state diagram. And this is also a state diagram. So we have different kinds of state diagrams for Moore machine and Mealy machine. Okay, so in this state diagram, it's actually very intuitive, right? If it's not intuitive, right, let me know ASAP. Okay, so which part is confusing you? So first, we have bubble. Okay, state bubble, right, like this. So this one is a state bubble, right? So usually we name each bubble, right? We come up with a name. Like in this case, we name the first bubble. Well, this is basic state. So for this system, we have 3 states. S0, S1, and S2. So we are focusing on the Moore machine here. Okay. So and each bubble represent a state. Okay. And we use we actually need to move between states, right? So think about flip-flop, right? So we have two states, right? 0, 1. So when we change d value, we may go from state 0 to state 1, right? So same thing here. So we may have this transition, right? We use this edge or arc between the bubbles to indicate the state transition, right? So these are the two key elements. So this is basically like a graph, right? So we have this node or bubble, and then we have the edges or arcs, and these are directed. Okay, so this arcs. Also, we put input value on the arcs. So basically, think about the state machine, right? So that's basically how we need to compute the next state, right? We need to compute the state transition, and next state depends on both the current state and the input value, right? So we put input value like this on the arc. I'm gonna reason about this, right? So I'm gonna give you a concrete example to let you know, like how exactly do we do the transition and such. Okay, right. Yeah, so I'll answer your question soon. And then we have bubble, right? So we have this bubble inside each bubble for Moore machine. So since for Moore machine, the output only depends on the current state, right? So for Moore machine, we directly put output inside each state bubble. This basically corresponds to what do we output for a given state, for a current state. And for Mealy machine, so we put the output, since output for Mealy machine depends on both current state, right, and the input, so we put the output on the arc. Then we usually have a slash to separate these two. All right, this is the state diagram in a nutshell, right? So there are some questions, right? First, I'm confused about arcs, right? If S0 can only output 0, how is there arc coming out of it labeled 1? Right, so we're talking about this one, right? We're talking about this edge, right? So very good question, right? So let me so give you guys, right? So so basically for each state, right? In this case, right, for each state, at each state, right? So every clock cycle will receive new inputs, right? So for this specific system that the state diagram is modeling, we have 1-bit input and 1-bit output. Right? This 1-bit input can be 0, 1. 1-bit output can also just be 0, 1, right? So what this diagram is saying is, when we are at S0, we output 0. Okay, first we output 0. That's a Moore machine, right? And then we look at the input. So if input is 1, like this, next cycle we're going to stay at S0. This is a self loop. We're going to stay at S0. Again, we have two combinations, right? So 1 and 0. So what happens if you see an input, right, being 0? So that's where, for this state diagram, so we actually need to go to a different state, S1. That's where we are changing state, right? Okay, so that's how the arc, right, is useful. So this arc, right, so you can use the arc to indicate that we are staying in the same state, or we make transition to the next state, right? So the arc basically tells us how to do the state transition. Okay, so it's not about why. So Taylor's good question, right? So why is one go back to itself? Right? It's basically how this specific FSMs works, right? Each diagram specify FSM. Okay, it's not like we always go back to the same state, right? Given input 1, right? Okay, so there are more questions, but let me maybe give you guys some example, right? So hopefully this will be more clear. Right? I'll try to walk you through some example. For Mealy machine, right? So again, in Mealy machine, so we only have state name. We don't have output in the bubble, right? And we also have the state transition, right? So we put this input, okay? We have input on the left-hand side of the slash, and this special output on the right-hand side. Okay, so if this is still too abstract, right? So let's go through example. So hopefully this will help you guys understand a little bit more about what's going on. So first, right? So same diagram, right? 3 states, right? So 1 input, 1 bit input, 1 bit output, 3 states. Okay, with bubble for each state, and arc, right? Specify the transition. Okay. So let's see. So let's say I give you the input. I give you this input sequence, 1 0 0 1. Right. And assuming that this diagram, we have also something called a reset. Okay. Assuming that and there's a reset that initialize the whole state diagram, the whole FSM. So it's initialized to state 0. So this is initial state. All right, so add this initial state at 0. So if I give you a sequence 1 0 0 1, can you guys tell me what's the state sequence? So at S0, so we are seeing a 1. So what is the next state? So we are starting from S0, right? Next state, S0, right? And so we are done with 1, right? Okay, so we can also look at the output, right? Initially, we are at S0, so we output 0, right? So next cycle, we also output 0, right? We stay at S0. So now we are seeing a 0. So where do we go? Right, S1, right? And we continue to output 0. Okay, and another 0, S1 again, right? Also output 0. So now we are seeing this 1, okay, the last one in the sequence. So we go here, right? We go from S1 to S2, and we output 1. Any questions about this? Any more questions about how the transition works? Okay. Why are there 2 S0s? Oh, so good question. So this is my start state, initial state. I'm assuming that I'm starting from S0. Okay. All right. So can you guys sort of identify, try to figure out what exactly is going on here? Like what exactly is this FSM doing? It's actually trying to detect some pattern in your input string. You're accepting a string, right? A stream of input bits, right? So when does it output 1? When does this sequential logic output 1? If we just look at the transition patterns. Here, when we have 0 1, right? 1 0 0 1. So at a certain point we hit 1. So let's say I have another 0 here. Do we output 1? No, right? But if we put a 1 here, we see another 1. Right? Okay, so very good. So some of you are already seeing the pattern, right? So basically, in the string, right? If there's a 0 1 in the string, in the input stream, we output a 1, right? This FSM. This FSM is trying to figure out, to find this pattern. The moment there's this 0 1, okay, first 0, then 1, this FSM is gonna output a 1. Okay, right? So see here, right? You look at this path, right? 0 1, we output 1, right? So no matter where you start, no matter where you are, right? No matter which state you are in, you get there 0 1, right? See here from S2, 0 1, we output 1, right? And also S1, right? 0 1, right? We also output 1. So regardless of the current state, right? So if there's a 0 1, so this FSM is going to give you 1. This is a basic string, the pattern measure. Any questions about more state diagram, more machine? Okay. One thing to remember that later on when you guys scroll more machine, make sure you have the output in the state bubble. Right. So one more question, right? So where do we give the inputs, or is it just not part of the diagram? Right. So good question, actually. I think you are trying to figure out how exactly do we implement this, right? Okay. So for now, let's focus on this. This is actually an abstract model, right? So this state diagram is basically an abstract model. So this state diagram only tells you the behavior of the FSM, right? So it basically tells you at which state, right? If you're seeing certain input, how does the FSM respond to that input? And later on, of course, we're going to see, right? So of course, input, right? So will come from the input side, right? So we will have additional input. When we implement the FSM using sequential logic, right? There will be inputs coming in, right? The real inputs, right? Like reset is also one of the inputs, right? There will be real wires, real signals, right? Coming into the system. But this diagram is abstract, right? This diagram is not concerned about how we actually implement this, right? Do we use wires or what, right? Okay, so there's more. Right, so Mealy, I'll ask you guys to do a quiz pretty soon, right? So with Mealy, so make sure that you guys pay attention, right? If this is still not clear, right, just ask. So same, actually this is implementing something very similar. So Mealy, let's look at the same, right? In this case, we have one input, right? One output, but this is just two states, right? Bubble for each state. But in Mealy, we don't have the output in the bubble, right? We have output here. This is output. This is basically saying that, okay, so when we are at, let's say here, right, when we are at S1, right, when we are seeing input 1, so we will output 1. Okay, so this is what the notation is saying. Right, so same sequence, input. We were using 1001, right? Let's say we also start, right? So we reset the FSM, we start with S0, this is my initial state, right? Okay, what's the state transition? 1001. We go to what? But we can also look at the output. Okay, so from S0, so when we see a 1 right here, right? S0, we stay at S0, right? And we output, right? We output 0, right? So we're done with 1, right? You move on to 0. Okay, so that's why we're seeing this, right? So we make a transition to S1, okay, and we output 0, right? And next 0. Okay, so we are at the S1, right? We are seeing this 0, right? S1, we output 0 again until we hit 1, right? So that's where we go back to S0 and we output 1. Okay, so this is right, very good. So that's the S0, S1, S1, S0. That's how we read Mealy. What is this Mealy diagram doing? What is this FSM doing? It's also detecting some pattern. I can clear this for you, just in case this is too noisy here. Same thing, right? It's also detecting 0, 1. Right? Anytime there's a 0, 1. So see here, there's a 0, 1, 0 here, 1 here, we output 1. Okay. It's also some kind of a string pattern metric. Any questions before we do the quiz? Okay, so let's look at some real examples, real problems. So usually this is how we use FSM. Right? Again, what we are interested in doing is to solve real world problems, right? So usually, we are given some problem. So that's usually described not in the digital language, right? This can be described in English, right? So that's our problem statement. And so that's where we will try to analyze, right? What are the inputs and outputs? What are the states? And we try to first come up with this abstract state diagram. Okay. And then we try to determine the hardware implementation, right? So for the rest of this lecture, we're going to focus on the first two steps. In the next lecture, I'm going to talk about, right, how we actually implement circuits, okay, including Verilog. So first problem, you guys already saw some pattern detector, right? Let's look at another one. Okay, let's create our own. So we are given an input stream, right? So 0, 1, right? We have 1 bit input, 1 bit output. So what we want to detect is 1, 1, 1, as simple as this. Okay. And we actually want to allow overlapping patterns. So what do I mean by this? Basically said, so see here, so I have 4 ones right coming in. So this is the input patterns. So by allowing overlapping patterns, I mean that for this 3, so we have 1, 1, right? So this is where out is going to be a 1, right? But we also allow this overlapping pattern, right? So we don't reset the FSM. So see here, so we also have, when the next one comes in, you can also combine with the previous 2 ones, right? So this is where we output another one. Okay. All right, it's clear. So this is the problem, right? So we want to detect 1, 1 as simple as this. So let's draw the diagram. Okay. Let's start with some state, right? For sorry, somehow. Let's start with some state, right? We usually name the state, right? Let's call the first one init, right? This is how we, right, initialize. So when we reset, we arrive at this state. Okay, in this state, right, we haven't detected anything interesting yet, so we output 0 in the first state. So at this state, if we are seeing a 0, what do we do? You are seeing 0. And trying to draw an arc, you see a 0? Yes. Self loop, right? Because there's nothing interesting. We want 1, 1, right? We want to see 1. So when we see a 1, okay, so the thing on the arc is the input, right? Then we see a 1, so we get something interesting, right? We are making progress. So that's where it's time to advance to another state, a new state. Okay, so let's just call it got1. For that. So what do we put in the bubble? What do we output? 0, 1, 0. Very good, right? So we're already done with this, right? So we're already done with init, right? Okay, so we have already handled both combinations, right? 0 and 1. We're already done. It's already a complete state. So same thing for got1. So when we see 0 for got1, what do we do? Do we stay or do we go to somewhere? Right, we don't want to stay, right? So we want to go back to init, right? We reset basically. We go back to the first state. So it's 1, then we are making progress, right? We are seeing the second one. We start another state, maybe create another state, got1, 1. All right, so we're already done with this, right? So we're done with got1. So we handle both inputs. So now it's hopefully clear, right? So got1, 1. So when we have a 0, we also go back, right? Okay, and when we see another 1, so we should output 0 here, right? Got1, 1. Right? This is where we have everything, right? Got1, 1, 1. So what do we put in the bubble? 1. Okay. So at got1, 1, if we have a 0, where do we go back? All the way, right? 0. And if you see a 1, do we go somewhere or we stay? If you have a 1, we just need to stay, right? Remember, we want to detect overlapping, right? Overlapping sequence. So we output 1 here, and we also output 1 here, right? Right. Because next cycle, if we see a 1, we also want to output 1, right? If we see another 1, we keep right. So producing 1. All right. So there's more questions. If not, let's look at Mealy. Okay. So Mealy, same thing, right? Init, right? We reset it here, right? But we don't want to put anything in the bubble, right? For Mealy. So, but what do we do? So when we have a 0, we stay here, right? but we also output 0. This is Mealy, right? And if you have 1, we got 1, right? So again, we don't have put anything in the bubble. So we just look at the state, right? If you have 0, we go back, right? Output 0. If you have 1, we go to a new state, which is got 1, 1. Right? Make sense? Sorry, make sure. Right? We output 0 all the time, right? All the way until we go to got 1, 1. So got 1, 1 is actually the more interesting state. So when we have a 0, this is not too interesting, right? Right? We get 0, so we go back, reset, right? So output 1, output 0. So when we have a 1 in this state, got 1, 1, what do we do? Do we go to a new state, or we do something else? This is a Mealy. New state or stay? We can actually just stay and output 1, right? So this is actually, Mealy is somewhat more expressive, right? Since, it actually depends on, the output depends on both input and the current state, right? So we're done, right? Actually, with Mealy in this case, we get away with 1 fewer state. Okay, actually there's pros and cons, which is something that I'm going to discuss later on, right? But this machine implements the same function, right? Where we detect a 1, 1, 1. All right, so this is the first problem. Right? Hopefully this is not too This is not too difficult. Right. Next one. Let's look at the case where we have 2-bit inputs. Okay, so we are looking at the push button lock. Right. I have 2 buttons. Okay, 2 bits, basically S1, X2. These are 2 buttons. What this problem is saying that we actually need to input the sequence. Right. So we have an output cut UL, means unlock. Okay. We unlock when we see this sequence, when we see X1 buttons push, followed by X2 button, and then X2. Right? We basically push X2 twice. We push X1 button once and push X2 button twice. Right. So this is everything's in English, right? So all the problems so far has been described in English. So we actually need to encode it somehow. We need to encode the inputs, right? So we have 2 buttons, right? X1, X2. So we will just use 0, 0 to indicate that we did not push any of the button. Okay, 0, 0. Neither button is pushed. 1, 0 means X1 is pushed. Okay. And the left bit means X1. The right bit means X2. Okay, 0, 1 means X2 is pushed. Otherwise, if both buttons are pushed, we reset the lock. Okay, we relock it. Okay, we lock it again. Okay, is it clear, the problem? Right, a simple problem, right? But the whole point is to look at a 2-bit input case, right? So we have 2-bit input, still 1-bit output. All right, so now let's look at how exactly do we do the Moore machine, right? First, init, right? Again, we can do init. Right, so what do we output here? 0, right? Unlock is 0. Okay. So now we have 2-bit input, right? So how many combinations do we need to handle? How many input combinations? 4. We have 4 cases to consider per state, right? So later on when you guys draw FSM, first ask yourself, right? So are you done with the state? Just check the input combinations. All right, 0, 0, not interesting, right? 0, 0, we stay, right? Anything else? So what are the other combinations that we should put here? So the only interesting thing is, so we are expecting X1, right? X1 is 1, 0. Otherwise, other inputs in this state, right, is not interesting. And so with 0, 1, right, of course 1, 1, right? 1, 1 means reset. Okay. So when we see a 1, 0, that means x1 is pushed, right? X1 is pushed. So that's where we get to a state. Let's just call it x. Let me save some space for the output, right? Output is still 0, right? It's not unlocked yet. X1. So we also have a self loop. Maybe we don't. Do we need a self loop? Yes. Then 0, 0, right? Nothing happened, right? So 0, 0. So we stay. What do we expect here? From x1, we want to see x2, right? So we may want to go to a new state when we see x2. X2 is 0, 1, right? If we do not see 0, 1, also if you do not see 0, 0, if you see 1, 1, what do? We reset, right? What about, so look at x1, right? We have handled 3 cases, 0, 0, right? Nothing happened, right? Idle, right? So of course we stay. 0, 1, we go to the next state. 1, 1, we reset, we go back to init. What about 1, 0? 1, 0 means x1. Do we stay or go back? Okay, right. So actually, so this is where, okay, I actually intentionally leave something undefined here, right? It can be either case, right? So you need to think about, so this is the sort of password, right? This is a lock. It makes more sense to reset. Does it make sense, right? If some guy, right, enter x1 twice, it means that this guy does not know the password, right? It makes more sense to reset, right? Okay, but of course, right, this is actually part of the things that's not defined, right, very clearly. But in this case, let's just say we reset. Okay, agree? You can also say like if we detect the overlapping pattern, right? So then, right, yes. So in this case, overlap pattern is not considered. Very good, Steve. Yes. Okay, so now let's look at the next state, right? Let's call it x1. We got x1 and then x2. So what do? We output 0, right? And we also stay here, right? 0, 0. Nothing interesting, right? Go back, right? 1, 1, right? And if we see, we are expecting x2, right? So we want to see x2, right? So we want to see 0, 1, right? X2 is 0, 1. So this is, we want to go to the next state, right? So 0, 1. So we are just missing 1, right? Combination, which is 0, we are 1, 0 here, right? Same reasoning, right? We expect to see a password, right? So if you see x1, x2, x1, we reset. All right, so last state, right? x1, we got x1, we got x2, we got x2, right? So this is where we output 1, right? So, and the lock is going to stay open, right? The lock opened now. So I'm assuming that we only go back to lock state when we see 1, 1. Otherwise, the lock is already open. Okay. Otherwise, we stay here. The lock remains open. Okay. Until we reset it. Make sense? Okay. So this is more machine. Right. So if there are no questions, make sure you help me double check. Right. I'm going to show you the complete diagram next time. But help me double check. Right. In case I miss anything. Okay. So last one, Mealy. So this is going to be the last exercise for this class, for this specific lecture. Okay. So again, we start with init. We're doing Mealy, right? So no output in the bubble. Okay, we have the self loop, right? So we have 0, 0, right? 0, 1, right? So we really want to see x1, right? X1 is 1, 0. Okay, so otherwise we output. So see here. So I'm putting the output, right? UL. So over here, I have this slash, right? Slash means the slash separates the all bar, right? In the real bar separates the input combination and output, right? We output 0. Okay, so what do we output here? 1, 0. Do we output anything? Yes, right? 0. Okay, very good. Okay, then we go to x1, right? So very similar, right? So if it's 0, 0, right, we output 0. Okay, nothing interesting. Otherwise, first, we are expecting x2 here, right? x2 is 0, 1. So we are supposed to go to something new, right? If you see 0, 1, right? Otherwise, if it's not 0, 0, 0, 0, 1, 1, 0, 1, 1. So we output 0, right? Okay, the state, anything in the state, x1, x2. So again, we had a self loop, right? Output 0. So we are expecting to see x2, right? Which is 0, 1. So let's talk about what we want to do here. Okay, but so let's handle the other combinations, right? So we already look at 0, 0, 0, 1. We see 1, 0 or 1, 1, and we output 0, right? Okay, last state. Okay, x1, x2, x2. So, okay, just one more minute, right? What do we output here? 0, 1. Now we already have x1, x2, and x2, right? So we can actually output 1 right away here. Make sense? Right. We have already seen x1, x2, and the second x2. Okay. So what's missing is really, right? So we reset right here. All, we just stay, right? We are, I think we have 1, 0, right? 1, 0, and then we stay 1. We stay here. Did I miss anything? 0, 1. Right? Okay, any questions? It's clear? All right, we'll see this diagram again. Next time I'll tell you how to implement this, right, in the real circuit. All right, if there are no more questions, I think we're done. I'll see you guys in a week, right, on Thursday. Have a good break. Bye, guys.